really excited about the progress that's been going on in the online community, and all the progress that's been going on as far as completing quizzes and assignments. During today's program, we're going to have the audio and video off for everybody until the question and answer period begins. We do this so that kind of cuts down on the slowness of the Blackboard system. If we have too many videos or audios going, it kind of slows everything down. So we're going to keep the video and talk off for everybody until the question and answer period, and then we'll use a process of raising hands, and I'll turn people's audio on as you're asking questions. And also in the chat window, if we could keep the conversations to questions or comments about the program during the session, so that I can kind of keep an eye on that and monitor if there are any questions or things that need clarity. Okay, with that, I'm going to turn it over to Jamie, who's at Johnson.
Hello, everybody. In just a second, we're going to have Stu McClung join us. He is part of the Orion Crew Module Landing and Recovery System team, and he's an area manager and crew and service module. As part of the crew and service module team. He's going to tell you a little bit about the Orion program and what's currently going on with that. You're welcome to ask questions, obviously. If you'd like to go ahead and like Kathy said, we'll have the audio disabled, but if you want to post those into the chat log, we'll do that as well. And then he's going to actually provide some videos as part of his presentation, and we're going to go ahead and we'll post the links to those videos as best we can, so we're going to try to enable that functionality as well, but they won't be actually playing in the presentation. So with that, I'm going to go ahead and turn it over to Stu. We're going to go ahead and get started.
Good afternoon, everybody. Thanks for your interest. Just real quick about me, just so you know where I'm coming from. Engineer here at NASA. I've been here for 25 years now. Work landing and recovery, and I also just picked up the lead work for mechanisms and pyros. So I've got a lot of different areas I cover. Got a lot of different teams that work underneath me. The engineers that work for me now tell me I'm not a real engineer anymore. I'm as much an engineering manager as I am as an engineer. We just, of course, and I've got some. What I was going to do is kind of give you a little bit. Here's what Orion's doing today. Most of you know, I assume you know, we had a great test flight, EFT-1, back in December, and talk about that a little bit. These charts are just brand new, and the videos were embedded in them, and we can't quite get them to play on Blackboard. So Jamie's going to try to fix that while we go. And so I'm just going to tick through the charts and give you an overview, and we'll then do Q&A, and we'll get going. So just a little bit about Orion itself. You know, we are the deep space vehicle. We're the part of the agency program to go set up to allow astronauts to go explore deep space. And for us, deep space, the way I define it, is any destination really starting at the moon. ISS continues to operate in low Earth orbit. We've got crews up there now doing great science. International and commercial partners are carrying cargo and crew back and forth. Our job is to establish the capability for us to go deep space and do human exploration out there. And so this is just a quick view of what the Orion vehicle looks like. Launch abort system there on top, the crew module, the service module, the spacecraft adapter, and then the jettison panels. Where I spend most of my day is working on the crew module piece of it there itself. Moving on. Oops. No, I'm driving, am I? There we go. A little bit about our timeline. We actually had our first test flight back in May of 2010, Pad Abort 1, and that was really a test of the launch abort system itself. The intent with the launch abort system is to give the astronauts the ability to get safely off of the rocket in the event of an emergency on the launch pad or early in first stage. It's a big solid rocket motor. On any normal mission, it's along for the ride, and then at 500,000 or 600,000 feet in the atmosphere, it's jettisoned off and drops back into the ocean. If there's an emergency, the computers sense there's an emergency, and it basically pulls the crew module safely away from what would be a fireball below it. You see EFT-1, we just flew that back in December on top of the Delta IV Heavy. And then our next mission in our timeline is EM-1. another uncrewed mission sitting on top of the first SLS vehicle. Then we have another abort test plan we call AA2, and then EM2 is the first human mission. And I'll get a little more in the charts to talk about what's in the various what's in the mission profile, and I can always talk about it more if you just pop me questions. Let's see. Hang on a minute. My page just went funky. I'm sorry about that. Yep. Pause. So well, the computer's misbehaving for me. Let me talk about it. There we go. Thank you. And that's just a picture of what I was going to do. Is we built this vehicle. We got it assembled. We got it tested. The way this is structured, it tries to tell a story. And this was a picture of the primary structure. In fact, that's the primary structure for the windows are installed, and that's one of the individual structural components that was welded into the structure. And when we keep going, that is the completed pressure vessel. It doesn't have the traditional shape that you're used to. But this green part, and that's the coropon on the vehicle that's used for corrosion prevention. That is the pressure vessel. That's the part of the vehicle that keeps the astronauts safe, keeps them in a pressurized volume. The cone panel that was on the last page is just one piece of that. That's all welded together. That's down at our facility down in New Orleans at the Michoud Assembly Facility. And then now it's moved down to the Cape. This was about a year ago when we started installing wire harnesses and doing other work on it. And we've kept going. This was the heat shield. Heat shield that we built for EFT-1 is actually the largest heat shield of its kind built ever. Our vehicle is 16 feet in diameter. The Apollo capsule was 12. This is a view of it as it's being prepared and worked on up at the facility up in Textron up in Boston. We used the same ablative surface called Avcoat that Apollo used. We looked at a lot of different approaches, ended up settling on Avcoat as the ablator that we wanted to use. The leading edge of the vehicle on the hottest part of the mission can see 4,000 degrees Fahrenheit. And there's very few materials that can handle that kind of heating. Avcoat gave us the combination of thermal and mechanical properties that we needed for the mission and that we'll need for our long-term missions. Here's a picture of the vehicle. It's mostly assembled now, and that heat shield that was upside down in the other picture is now hanging underneath. There's actually this silver tape that you see in the picture was installed primarily to help us with on-orbit thermal management. The heat shield, for as good as it is, it likes to start warmer than colder, if you want to think of it that way. And this very thin layer of aluminum tape actually helped us basically manage the heat transfer coming through the heat shield. And so it's not quite done there. Not all the strips have been involved. It was pretty funny. I was down in Florida when we were doing this work, and one of the technicians working on it was laughing that he never thought he'd have to install wallpaper on the spaceship, but it felt like he was laying on, these are like, each one of these strips is about 4 inches wide, so he was laying up 4-inch strips of wallpaper. That tape was some of the first stuff that burned off as we're coming into re-entry. Another part, this is the service module portion of the vehicle. It does not have its fairings installed yet. The fairing is over there on the left-hand side. Fairing jettison was one of our key test events during EFT-1. For EFT-1, we built the service module here in the States, starting with EM1 and EM2. We're actually partnering up with the Europeans, and part of the service module will be built in the States, and part of it will be built by the Europeans and provided to us from European Space Agency. So we've partnered up much like we've done on Space Station and continued our international partnerships together. Here's another shot of the vehicle a little bit further along. The service module underneath it is now complete. The black tile that you see are the back shell panels. The heat shield is no longer visible in this view. You see the back shell panels. Those two reddish patterns, those are the window covers from that original panel I showed you back a few pages back. This is in our final assembly and testing. We were doing our final checkout of the vehicle before we rolled it out to be stacked on top of the rocket. we're actually, this is a view of the day we stacked the crew module and service module on top of the spacecraft adapter. And now it's moved over to the other building where we're taking the launch abort system that we flew on EFT-1 and stacking it on top of the crew module. And it gives you a sense. And again, this crew module is sized for, as I said, it was 16 feet in diameter, sized for a crew of 4. We have a version that can handle a crew of 6, but most of our missions require 4 astronauts. And this just gives you a sense of scale when you put that launch abort system on top. And that was the evening of, actually of Veterans Day. That was the night we rolled, that's the completed stack with the service module underneath, and the crew module is covered underneath the launch abort system. And that's being driven on a crawler. We paused at the VAB, the Vertical Assembly Building, on its way out to the launch pad. I was there that night. That was a lot of fun. We got that done. Actually, took we had a 1-day delay. It turns out that even as you look at the size of that building, we have to deal with things like winds, lightning. Can't have any lightning in the area. Don't want to take the chance of a lightning strike on the vehicle. And so you have to, when you start moving vehicles like this around, the weather forecasters become an important piece of the operation. And here's some pictures from stacking. The United Launch Alliance was the company that we actually bought the ride from in this case. Typically NASA, and for EM1, we'll be building our own vehicle. EFT-1 was a little unique in the sense that we partnered and purchased a launch from United Launch Alliance, the Delta IV Heavy, and we delivered our payload to them, and you see the team in the process of stacking the bottom of our vehicle to the top of the United Launch Alliance booster. And there's a picture of it out on the pad. Video's up and running yet or not? Okay, hang on a second, because so if we get it to work, the upcoming video is a set of launch footage. We'll see which one comes up, and then I can talk through the video. The charts have a set of videos embedded in launch footage, and then the re-entry and landing footage. All right, so we're still having some technical challenges getting that loaded. We'll keep working on it. I will keep going in the meantime. We're taking me back to main page. Here we go. I can tell you, I had the pleasure and privilege of being down at the launch. I was working some media operations that day. For any of you that if you ever have a chance to go to the Cape and watch a launch of any kind, not just ours, it's pretty impressive to see something zipping off the face of the Earth and breaking, leaving gravity behind. It's well worth the trip. The mission went quite well, and let me talk off of this page for a minute while see if it gets loaded up. So EFT-1 was a two-orbit test flight for us. We launched out of the Cape, did the first orbit, and then had the upper stage that you see pictured there on the right or on the left of the page. Upper stage burned, and that gave us a nice high elliptical orbit and took us out to roughly 3,000 miles or so off the face of the Earth. Nobody's been out that far really since Apollo. Space station orbits at couple hundred miles up, so we were well above where space station orbits today. That the Delta IV Heavy has the energy to do that for us, give us that capability, and by shaping our orbit that way, we were able to have a very hot reentry, which was one of our test objectives, was to take that heat shield and test it and try to stress it. able to get an entry energy that's roughly 80 or 85% of what we'll see on a normal deep space return. Heat shield, something of that scale, you can, when we're testing in the lab, we can test a 4-inch diameter puck in an arc jet. One of the key aspects of the reentry is really testing acreage. You run these arc jet profiles and you heat the test article up to the entry heating that you expect, but you can't achieve that over the entire surface. And so now you take what you learned in the lab and what you've analyzed to, what your predictions are, and then you go, in this case, do a test flight. And the vehicle had 1,200 different sensors embedded in it. 200 of them were in the heat shield to measure the temperature extremes that the heat shield saw, both on the hot side and on the cool side. And so we've got all that data back now. We can start comparing our predictions to what the actual temperatures measured were and feed that into the next design. And so if it turns out that it performed better than we anticipated, maybe we'll be able to use that and inform our next design and take some weight out of the vehicle. For us, mass to orbit is crucially important. When you're going deep space, every pound you can get off the vehicle you can apply to science, or you can apply to crew supplies, something like that. And so we're always looking to make the vehicle safe enough for the astronauts to do the job, but not have any extra weight sitting in there. And so flying a test flight like this gives you the data to make informed decisions and make that happen. And then we landed off the coast of Baja. And this is just a little pictorial that shows the various separation events, or the various test objectives we were looking for. We had a number of separation events. The panels separating off the vehicle. The panels have to come off, otherwise on a normal mission you cannot get the heat shield, or not the heat shield, you can't get the solar rays deployed. If the solar rays don't deploy, you're going to have to come home early, because that's giving you the energy you need for your on-orbit activities. All the heat shield measurements. The vehicle also went back and forth through the Van Allen radiation belts, and so all of the computers on board got a good dose of radiation. All of you have either an Android or an iPhone or something like that. Extremely capable, extremely powerful. They're also not hardened for space radiation. And if you were to take your phone out to deep space today, it would get zapped. It would die, never work again. So one of the things we did was, the computers are all hardened, and we were looking to make sure that, as we predicted, that the vehicle would operate the way you expected it to. As you can imagine, when you start your reentry at 20,000 miles an hour, and you have a very specific trajectory you're going to fly, if the computer wants to lock up because it got hit by radiation, you're going to lose the vehicle. Can't allow that to happen. And so we've tested them in the lab, and the test flight was proof that the avionics did what we expected. We actually did see a couple of minor single event upsets, as we call them, and then everything recovered and it worked just fine. And the parachute system is one of the things I work on a daily basis. After you've come down through the atmosphere and burned off the speed by sliding through the atmosphere and letting the friction of the atmosphere slow you down, parachute sequence starts at around 25,000 feet and around 300 miles an hour, and we had good parachute deployment. Most of our parachute testing is done out in Arizona. This gave us a good test flight, starting with a deep space environment and then finishing and landing up on the water with a full-up system. More video that's just, I guess I'll just keep on going, Jamie.
What we're going to do is at the end we'll go ahead and we'll show the videos.
All right.
All right,
Let me keep skipping past the videos. Most of these videos are now available on our Facebook page. Let me stop here. This is a video, but I'll stop for a minute. This happens to be a still shot. So that's the crew module out there in the distance. This was taken off of the anchorage, off of the recovery ship. We're under 3 main parachutes. Again, as a point of reference, each of those chutes is 116 feet in diameter. When we're landing, our touchdown velocity is, and our requirement is to give the vehicle a touchdown velocity of 25 feet per second, so roughly 20 miles an hour. The vehicle at landing weighs in the range of 20,000 pounds, so it gives you a sense. We start our sequence with what we jettison the forward bay cover, and then we put out what we call 2 drogue parachutes. They start the deceleration sequence. We actually cut them away. 3 small pilot chutes pull these 3 big main parachutes out of the vehicle. They are stored up in the top of the vehicle. They open up through their reefing stages. We basically open them gradually, and then we get on our final descent. And this is a shot just before splashdown. So this is, again, our timeline. So, hey, we've landed. What's next? All right. We laugh about it at work. What have you done for me lately? It was a great mission. We had a great time. A lot of success. That's great. Now we're off, and we're actually already working on building hardware and buying parts and improving the design that will fly on EM1. So we're continuing on. We got to celebrate for a day or 2 or 3, and then we have moved on. Let's start working on the next one. And just a couple of shots about what's the difference between low Earth orbit or space station, what we're doing today, and deep space, because that tends to, it's a different mission. It drives what we do. When you're flying on ISS, if you need to come home for whatever reason, sick astronaut, it's time to come back. As you see, it's about a 45-minute return. You can get home relatively quickly, and it allows you to, in many cases, choose when you choose to re-enter. If you think about the space shuttle, if we had bad weather in Florida, we would delay undocking from the space station and delay the return a day so that we could make sure we landed in good weather. For our missions, when you're going out to the moon or even further, you're looking at multiple days. When you decide you're coming home, you've done your reentry burn, if you want to call it that. You've done your return burn. We're not like Star Trek and Star Wars and all that good stuff where we can zip around. The physics and the capability doesn't really exist yet today. It exists on TV. It doesn't exist in reality. And so you choose your reentry and your landing day multiple days away. That has some different challenges. You've got to design a vehicle that can be able to handle a failure, so you get the crew home safely. Right? It gives you different. You have to deal with, for example, a micrometeorite debris penetration. How long, if you puncture a hole in that green structure, how long do you have to keep how many hours do you have to keep feeding that leak? Right? If you've developed a leak, it's going to continue leaking until you get out of vacuum. You have a 45-minute leak to deal with from space station. You have multiple days, and so that sizes how much oxygen you carry, sizes how much shielding you put on the vehicle. It goes into those levels of design detail. And this gives you just another view, another idea of some of the differences you have to deal with as far as mass, how much food you have to carry. I had a 5th grader one day ask me how much food it takes to go to Mars, and I frankly didn't have any idea. This gives you just visually an idea of how many cubic feet of storage space you need for equivalent astronaut sizes going back and forth to a deep space mission. Volume becomes a real challenge. So for a mission to Mars someday, the Orion vehicle will be the vehicle that the astronauts would launch in, they'd land in. There will also be another module or 2 traveling along with them. If you think of a space station lab module, I did a quick back of the envelope thing one day and figured out that for the food back and forth, just the food, not the water, but for the food volume going back and forth to Mars, it looked like a small U-Haul truck is kind of the volume that you need to carry all today's freeze-dried packed food. So volume and again, all that volume and mass, you got to get it off the face of the Earth. So shrinking things, making a vehicle as light as it can be, ends up coming back to what we're looking at and trying to achieve in our technologies. And I mentioned before, we continue in our international partners, working with the Europeans. And this is just a cartoon of what SLS will look like. If you look there, you see the Orion sitting on top of the stack under the launch abort system, and then the big booster down underneath the Space Launch System. For folks that are familiar with Apollo, scale-wise, we're very comparable in size to what Apollo looked like, and big, tall, massive rocket. So it'll be an impressive launch when we get there. And so yeah, what we think about it, we've taken our first step. We're headed off to Mars, headed off to the Moon. Orion, the vehicle, is flexible enough that I like to tell people, you pick the destination, we'll take you there. You know, we're building something that can take us to any of these deep space destinations. We just have to eventually you have to pick that destination and it sizes some of your consumables, but a lot of what we've done so far supports any of those missions. And these are all of our social media links, and that is actually the end of the presentation, so I'm going to go try to do videos.
Okay, folks, so the videos that Stu was referencing are actually on the NASA Orion Facebook page, and we're going to encourage you to go there and check out the videos. You actually can scroll down there on the left-hand side of the page, and we're not going to be able to play those for you because you'll get some of the video, but it will be the time delay in between that and not having any sound. You won't obviously be able to see them as we would like you to see them. So we encourage you to go there. What we're going to do now is we're going to spend the remaining part of the time, actually you can ask questions of Stu. The way that we're going to do this is we're going to actually have you guys prepare your question in the chat box, and then when I call on you, we're going to go ahead and actually allow you to, once I call your name, you'll go ahead and actually click enter once I call on you. So if you have a question, we're going to go ahead and have you actually raise your hand. The raise the hand icon is just underneath your name. And before you raise your hand, though, go ahead and type it into the chat box. Once you raise your hand, I'll go ahead and call on that person, and then you can go ahead and click enter. And then that way we can go ahead and keep track of it a little bit easier that way. That way people aren't overloading the chat box with the questions themselves. So wait for me to call on your name, and then call you, and then we'll go ahead and go from there. So, all right, first up is going to be Clayton. So if you want to go ahead and submit your question, Clayton Palmer. There you go, Stu.
Okay, so do you have to layer the tiles differently based on entering different atmospheres? You don't layer them per se differently. You do size them differently. Let me think through it. So on the underside of the vehicle, particularly on the heat shield on the hottest part of the surface, try to minimize steps and gaps and joints. Any kind of a step and gap or a joint is a potential weak spot. And the heat shield itself is actually a honeycomb mesh that is bonded to the skin below it, and then the avcoat is actually gunned into it, sort of like a really fancy caulk gun, if you want to think about it that way. Up on the back shell, the tile thickness is sized by the appropriate, by the heating at that different tile location. And if you look really close at the pictures and the photos of it, you'll see that I want to call it not the layers, but the pattern that the tile is laid up in is laid up intentionally to minimize a gap between two tiles running parallel to the expected flow field. Maybe, I don't know, let me know if that answered your question. If not, come back at me.
Okay, once again, folks, I'm going to call on you, so please do not submit your question. Just type it into the chat box, and when I call your name, then you can go ahead and press enter, and then that way we can moderate things a little bit easier. So we're going to go to Sean Dysinger. Sean, you're up next if you want to go ahead and enter your question. Okay, and actually, let's go ahead and go back to follow up on Clayton's question, and then we'll go to Sean. It's right there for you.
Okay, is there a pattern for entering both Mars and Earth? I assume that the pattern that we lay them up in is the same. I actually don't know that for a total fact. I would expect that you'll take whichever, so in the Mars entry would be the hotter entry, and we would tend to design the thickness of the tile for the hottest case. Just one other side note, one of the things that actually sizes the thickness of tiles is a micrometeorite debris environment. You can't have holes in this tile from an MMOD hit, because then you've got a potential flow pattern. Think of what happened to Columbia, right? You want to have a good solid surface on the outside. Space Station actually has a fairly severe MMOD and space debris environment, and that makes the tiles thicker than they would necessarily have to be just for the heating part of the reentry of the mission. So those are the kind of factors that go into it. Pattern a little bit, but generally it's the environment. What's my heating environment and what's my debris environment? And you blend those two together and use that to size the thickness of your tile. And again, you make them as skinny as you can, but leave yourself enough margin to handle the predicted thermal environment.
So Sean Deisinger's question's up next.
All right. Appreciate the good work there, or good words about EFT1. EFT1 was pretty amazing. Radiation mitigation. How the system's hardened. I know a little bit about it. The structure of the vehicle itself provides some level of protection. And then there are some coatings that are put over the boards and the components that are built up. Frankly, I don't remember what chemically that's made up of, but they do put a conformal coating over top of some of the components to help give them a layer of protection. And then we take them up to places like I know Indiana University is has a big radiation lab. It's one of the areas that we use. There actually was a student experiment. I almost forgot about that. There was there was a competition, and there was a group of high schools around the country that competed, and one out of Hampton, Virginia won. And so they flew radiation sensors that they got to fly, so along with their data, we'll get other data to give us good measurements of what the radiation was really saw. And actually, just one more thing on radiation. One of the harder things to deal with is radiation protection for the crew. We can clearly, we demonstrated on the FT1 that we've got the vehicle protected. Long-term radiation exposure, like for a Mars mission and back, and making that light enough that it's not massively heavy and keeping the crew safe is still quite the challenge. You can jacket the vehicle in water if you wanted to. You could wrap a lot of lead around the vehicle. That all gets heavy. We're still looking at how do you do that without getting overly heavy. Processor speeds. I don't think I can't give you good processor speeds, although one of my buddies did tell me that we are not flying anything that has a processing speed of an iPhone 6, right? It's still, by today's phone standards, it's fairly archaic, but it's also very much hardened, and it's tested and reliable, which is really the trade you end up having to make for something like this.
Okay, Heidi, you're up next. If you want to go ahead and enter your question into the chat box. Okay. There you go.
Yeah, parachute driven. I can talk about parachute loads quite a bit. So you're coming back to the atmosphere. The vehicle's falling. Gravity never takes any time off. You open them. The vehicle's traveling at 300 miles an hour. You've got the dynamic pressure, which is just the byproduct of falling down through the atmosphere. You open these parachutes up, and they're grabbing air, and that interaction, that activity is creating the load that the parachutes and the vehicle sees. It's the air pressure that's there. If you for example, right, if you open the parachutes up in a vacuum, there's nothing there, and so there's no load. You're down in the atmosphere, and actually one of the things that we work on testing is testing at a relevant altitude. Right, the air pressure at 30,000 feet is different than the air pressure at 5,000 feet, and so we do our best since our entries start at 30,000 feet, when we're doing our aircraft-based testing, we push the test article out of a C-17 at 35,000 feet and let it start to fall and get on test condition. So usually it's at 20,000 feet by the time we're actually starting test sequence, and we have to interpolate the difference in air pressure and vehicle speed and rate. But yeah, we talk about it, and people refer to it as Q. When we're on the maximum load that the parachute sees is maximum PSF, pressure per square foot, per pounds force per square foot, and we talk about that as Q. And the balance is opening in stages. You can make the parachutes extremely strong, then they get heavy. And if you make the parachutes strong enough and open up and slow down really fast, that load transmits through the risers that are connected to the top of the vehicle, and that goes into the structure of the vehicle. And so that's why we open them in stages. Basically, think of hitting your brakes slowly as opposed to hitting the brakes hard. And use that to slow you down and basically manage those loads.
All right, Michael, you're up next.
Yeah, sorry.
Now you're going to have to go ahead and type in your question. And if Caleb, if your question's ready, go ahead and send that over. Michael's trying to get his all situated. We'll come back to you, Michael.
All right, tech problems while we ran into making the heat shield. Let's see, a couple of real interesting challenges that we ran into. First, we tested about 8 different materials. Let's go back and look at how do you make which one works the best. Apollo flew Avcoat. We ended up settling on Avcoat. It's the same material. We'd used it once before. When they made the first batch of Avcoat, it failed miserably. The chemistry between the mid-60s and 70s, and now processing slight differences in chemicals caused it to fall apart in the arc jet test. Took them about 6 or 9 months to get the formula tweaked and right, and then they got that fixed and got it working just fine. And then the other challenge we ended up having with the heat shield was when it was curing, you put the Avcoat into the honeycomb and basically put it into a giant oven. Think of so you got your thermally conditioning, you're baking the cake. We had some microscopic cracks where it was debonding from the structure underneath, and losing bond strength is something that we're really worried about. We actually had to go in and basically drill the cracks out, fix the cracks, basically do a core repair and eliminate that. So those were probably the technical challenges on making that happen. Those were the 2 biggest ones. Both of those got solved through the engineers being creative about how you eliminate that. And then the heat shield itself is structurally attached to the bottom of the structure with 60 shear pins. And so you can imagine 60 1-inch dowel rods, metal dowel rods, being press fit into the 60 holes that were lined up for it. Extremely tight tolerances. That actually came off without a hitch. A lot of work went into getting ready to do that, but that kind of a tight tolerance was a real challenge to make sure we were ready. Roughly, how does it work? An ablator effectively is bubbling and burning away. You're throwing material away. As it gets hot, it'll start to melt away, if you want to call it that. And as it does that, that takes the heat with it. Tile will resist the flow of heat. They're really good. They're good insulators, if you want to think of it that way. But an ablator, actually, you're giving up material in an expected time frame, and it just takes the heat with it and turns it into plasma that goes past the vehicle.
Okay, folks. So we've got quite a few questions. So we're gonna Stu's gonna try to go them pretty quick through them pretty quickly, but there are 40 people online to ask questions, so we're going to try to knock out them as best we can, but just be aware that We might not get to all the questions. So we're going to go to Michael next, and then Alex, and then Kay Goodson. So Michael, if you want to go ahead and submit your question, and Stu will try to give you a quick answer to the question.
You telling me to talk faster?
Let's see if we can get Michael's question. There we go.
Okay. It's like part of the sentence didn't err.
Yeah, it looks like we
help me out, Michael. It looks like part of the question got chopped off.
Okay, Alex, if you have your question, go ahead and put that in while Michael's working on that. Good, there we go.
Competitive to become a NASA engineer. Let's see. Oh, getting master's in mechanical engineering. So I did not. I am a. Let's see. Got a bachelor's in engineering. I never went back to get a master's. I actually ended up at NASA almost not by intent. I started working aerospace, and then the opportunity came along to come in. It's hard for me to say how competitive it is. I know a lot of people I work with want to be here and worked for it, gosh, all of their career. I'll tell you what, my GPA was 2.7 as a bachelor's, if that tells you anything. So I wasn't the valedictorian of my class. So there's hope for anybody that's out there. Internships are a great way to get started. Between interning and co-oping, a lot of the people that we hire now have come in through the intern or co-op program. That is probably the best entry point. And that could be at any center. You start at any center or even some of the subcontractors and get that work experience. That definitely opens doors for you. And then it's funny because I still think of, and it depends on what you want to do. I started out doing basic drawing work and CAD and design work, and so a lot of people like me started at a vendor. I started at Rockwell, which is now Boeing, and then transferred over. And the industry base is pretty broad, and so that's not a bad avenue. You get started at a vendor and then get familiar with the NASA customers and change badges, as we call it.
Okay. Kay Goodson, you're up next.
Oh, okay, good. Whoops, it moved. Estimated weight of the heat shield. Oh, let's see. It's in the, I'm going off memory, 1,000, 1,500 pounds, something in that range. I don't remember exactly, but it's in that kind of ballpark.
All right, Chris McCauley, you're up next, followed by Danielle, excuse me.
Mission to the asteroid parcel. Oops. So the agency's approaching the asteroid mission really as a stepping stone to a Mars mission. It's easier from us because, and that's making the assumption that the agency will build an asteroid retrieval vehicle and bring it and put it into like a lunar orbit. Then use the vehicle to go up and use Orion as the vehicle to go up and inspect and do science on that asteroid. So if you make the assumption that the asteroid's already there in a low lunar orbit, that's an easier mission than Mars, primarily because of transit time. It's interesting. There's folks that the asteroid mission is it has its other challenges, right? You've got this mass that's probably the size of a small building. That has no gravity. It's there. You've got to fly up and rendezvous and get in proximity with this thing, maintain proximity, and then start your experiments. It's almost, that's got some different challenges than, say, going back to Mars, or I mean going to the moon and then using the moon as a test bed to go to Mars. Payloads and supplies primarily would be different because of the duration. You know, to get to Mars today with today's propulsion, you're looking at 6, 9, depending on where the planets are in alignment, you're looking at months to get out there. And so you've got to deal with all the consumables to handle say a 9-month transit just out to the planet, and then do your investigation in a 9-month transit home. Whereas an asteroid mission, and that's really the reason that the agency's kind of pursuing it, is it's in the range of 5 to 10 days to get to it.
Okay, Danielle, you're up next, and then we'll try to go back to Michael one last time, and then Ashley will be on deck. Danielle, go ahead and submit your question. There you go.
Time rough estimate when we send people to Mars. I think it'll be, I think our public, don't remember our public number, it's by 2030, I think is what the president has said. So my answer is by 2030 we'll send people to Mars, because that's what our boss has told us to do. Yeah, it won't be any sooner than that. The vehicle could be ready. I really think the biggest challenge is, as I mentioned earlier, the transit time. It's such a long mission, building the infrastructure to get out there and keep a crew fed and safe for a year and a half or two, and to get out. Personally, I would not want to just go fly out to Mars and do a flyby. I want to go out and get down on the planet and go explore. And so building up all the rest of that infrastructure and being able to afford that and being able to do it and keep crews safe is really the biggest technical challenge. But that's what we're all trying to do. And come on and join us and help us solve that.
All right, Michael, you get one last chance, buddy. Go ahead and submit your question. There we go.
That's okay. Oh, just got an answer. Okay.
There we go. Okay. All right. So
I got 2 for 1. Yay.
There you go. Ashley, you're up next, and then Dylan will be after that.
Let's see. Touch-sensitive instruments panels on board. You've got to protect against inadvertent contact as much as anything else. Any critical functions, we basically we put a software set in there so that you don't just inadvertently touch it. It's just like a lever lock, like a physical lever lock. You go in and touch, and it says, "Hey, are you really sure about this?" And you hit yes, or you slide your finger and adjust accordingly. And one of the other challenges we have is again, as I was talking about, number of days for returning home. We protect against the case that the crew module gets punctured by a piece of debris and it's vented out. The astronauts then get in their spacesuits, and so the spacesuits keep them protected from the vacuum. So you allow you don't allow it, but if you protect against the cabin going to vacuum, they get into their suits, and now you got these nice big gloves, basically EVA gloves, and you've got to be able to manipulate a touch screen in that glove as well as bare hand. And so blending the two of those and then making it fit on the panel and making it reliable ends up being the real challenge with the touch screen. And then we have a handful of physical switches as well. We just minimize it to only the critical functions.
All right, Dylan, you're up, then Timothy, and then Cody after that.
Fiber optics at all? Yeah, actually, a lot of the data is now in fiber optics. Some fiber optics and time-triggered gigabit Ethernet is used in a lot of the data functions. The critical computer functions are still what I would call old-fashioned hardline copper wire, but a lot of the timing and a lot of the chat back and forth is done on that time-triggered Ethernet. And we, in general, all of our hardware is designed to be at a minimum single fault tolerant. If it's something that is time critical, like again, guidance or any of your entry or ascent related functions, you can usually withstand at least 2 failures and keep going.
All right, Timothy, you're up next, followed by Cody.
You got me on that one on launching off the surface. I don't know for sure. I would assume that if you think of what we did way back in the Apollo days. Same basic concept, probably with a solid or maybe a small liquid motor, and it'll be sized and take into account the reduced gravitational pull. Again, you got to launch it off the Earth and carry it all the way out there. So you're going to make it just big enough that it'll do the job to punch you up and off the planet. And then I would also assume that motor, or the initiation for that motor, if it's a single motor, you've got redundant commands coming to it. If you were to use a solid, once solids are initiated, they're going to give you a burn. If it's a liquid, you'll take that liquid combo, you'll take that into account and make sure you got the proper redundancy, because you can't afford to have a false start on that launch to get you back to the vehicle, to get you home to Earth.
Okay, Cody, you're up next, followed by Jessica.
Heat shield sensors were a variety of strain gauges, some accelerometers, standard, basically, radiometers were installed, and just some standard, temp sensors, skin temperature sensors, like you might be using in an engineering lab today. In general, they were all on the vast majority of them were on the back side of the heat shield embedded in the skin. We actually had some that were core drilled into the aft coat, so that as it ablated away, they picked up some of that heat rate and that ablation rate. So a small number were, I'll say, partially consumed, but in general, all of them were located in a manner that they all came back. We knew, you know what the thickness of the material is, you know what the predicted temperature on the back side of that the heat shield is going to be, and so that's the data that you're measuring and adjusting off of. How do you keep it facing planet side? There is, and in one of the videos, when we can get it to run, you can actually see, and it's one of the ones we posted on our Facebook page, it shows the plasma trail, which are really cool. You see the beginning of the reentry, and you see the plasma trail, and once that plasma trail is gone out of the visual range, if you watch it long enough, you'll see little white puffs going past the cameras, and those are reaction control jets. They run off a hydrazine, and the computer is sensing the positioning of the vehicle and using those reaction control jets and firing them to maintain vehicle position and keep the heat shield in the proper orientation. And so that the geometry of the vehicle helps to some extent, but you need those reaction control jets to finish off the control authority.
All right, Jessica, you're up next, followed by Jimmy.
Could be, yeah. Nuclear propulsion. That's one of the possibilities. Nuclear propulsion's out there. I don't think it is sized yet in a manner into a package that's, I'll say, small and compact enough that it's totally applicable yet today. That research is out there. Ion thruster engines is another thing that's being worked on. So I think we will take whatever, the agency will take whatever comes along, whether it be us or whether it be some other inventive person out there comes up with something and it gets applied. But today it's not that's not one of my discipline areas, and so I'm not aware of any near-term use of nuclear propulsion.
Jimmy, you're up next, followed by Vicki.
Scroll back down. Yeah. So we actually, our computer guys talk about a single event upset. When you get a radiation hit, we used to get those on the shuttle where you're watching the processor, you're watching the data as it's coming back, and you'll see a blip. You'll see a readout in the onboard data that tells you that instead of just a smooth transition, that it, instead of a 1, you got a 0. I'm oversimplifying, but we saw that. one of the things you're trying to protect for is, you know, you're going to get hit with the radiation. You want to be hardened enough so that even if you absorb some of that radiation in the vehicle, the processor keeps running. And so they noted 1 or 2. I don't remember the exact number, but they actually they noted in processor performance, and then it reset itself and kept going. Let me look at number 2. Very little. It's funny. I heard a little bit about Kerbal, but only in passing, so I couldn't answer that without just making a guess. So I probably shouldn't hazard a guess on that one. Sorry.
All right, Vicki, you're up next. So we've only got about 5 minutes, so we're going to try to answer as many as we can in the next few minutes.
Factors taken into account on entry angle. It comes back to heating rate. How landing accuracy, and a lot of it has to do with heating rate. It also, you look at the amount of G's that the astronauts are seeing. In our reentry that we saw in EFT-1, the vehicle saw somewhere in the, going off memory, 6 or 7 G's was the max G's that were pulled. And so you have human factors to consider. You know, you can't expose the astronauts to too many G's for too long a period of time. And then you try to find a sweet spot between all those other criteria and, you know, having an energy profile that you can manage, and then minimize your vehicle weight.
All right, we're going to go to Mark next, and then Bree.
Yeah, you're talking about exercise equipment. Yeah, I really tell you what, I saw a version of our vehicle that was set up that had a rowing machine in it back years ago when ISS was part of our mission profile. Very tight quarters. Frankly, I think that for our long missions, like a Mars mission, we'll take an extra module along with us. And think of like a lab module like you see on Space Station today. We'll carry an extra element like that. We'll connect the crew module and that element together, and that element would be where you would do your living and dining and exercising, so that you don't have to try to stuff it all in this vehicle and be too cramped.
All right, Bree, you're up next.
I'm trying to think. New ideas, experiments you'd like us to try? Oh gosh, I'd like us to do an experiment to convince Congress to give us more money. Write your congressman. I'm trying to think of what else is out there. We're pretty creative. Oh gosh. See, I'm a widget builder, so I'm probably not the right guy to ask. You know, the things that you need to do to make it more feasible for people to live long durations in space. I know, like our food lab that's just down the hall from me is looking at how do you grow plants. Can you take a garden with you, right? Something like that. You know, how do you handle the personal? I mean, it's a legitimate challenge to be. Think about it. Being in this capsule with a team of 4 or 5 people for months at a time. You know, we've got we've got experiments going on today already looking at that. I'm open to any. Tell you what, I'm open to any wacky idea. It's probably not too wacky, so keep sending them in.
All right, let's go to
artificial gravity. I like that. You know, I've seen that in the movies. I got a hunch that one's tough.
Let's go to one more question with Laramie.
Rockets after launch. In general, rockets, the first stages drop back into the ocean, depending on the approach. Sometimes you'll capture the solid rockets and they'll land in the Atlantic under parachutes. You'll take those and clean them up and refurbish them or reuse them. Something like the launch abort system, we drop off from such a high altitude that it just drops off and breaks up upon re-entry. Visiting ISS, the only way that exists today is, and I think the Russians are still doing it, you can buy a ride with the Russians. You know, NASA's working hard with the commercial space community to develop that. That could happen. It doesn't exist today, but that's actually not too far-fetched that you know, some of our commercial providers will be able to carry paying customers up and you're be able to go spend some period of time on space station, or there's a company called Bigelow Aerospace that's talked about building an inflatable module, and you could go up and like treat that as a vacation in a hotel. Never know.
All right, folks, so we've come to the 5 o'clock hour, and Stu can stay around for a couple more minutes. I know there's a ton of questions ready for him to answer, so he can probably answer a few of those questions, but what we're going to do now is we're going to go ahead and wrap up the formal part of this presentation. We appreciate everyone's attendance here today, and we really appreciate Stu coming in and sharing his wisdom and all the experience that he has with NASA here. So a couple things that I want to give you updates on, then I'm going to let Kathy kind of close things out, and then Stu will be around for a couple more questions, and we'll try to go through as many as we can until he needs to get out of here. But we will have some updates for the next subject matter expert talk, which will take place next week. I think it's currently scheduled for the 20th. That presenter had to actually change that date and time, so we'll update that in Moodle. I think it's going to be on the 22nd. We should have that update up on the site within 24 to 48 hours. And the main thing that you want to keep in mind is that we asked that Module 1 be due today. You know, if you haven't gotten to that point in time and completed that, you definitely want to look at getting that completed as soon as possible. That just helps with the time frame for overall in the online course. So keep that in mind, and keep checking Moodle for more updates. With all that said, I'm going to go ahead and throw it over to Kathy, and then as soon as she's done, we'll go ahead and let Stu answer some of the remaining questions with the few minutes that he has left.
Okay, just want to thank everybody for joining us today, and thank our presenter for a wonderful and informational talk. I think we all got a lot out of this and learned a lot of information about the Orion mission. Thanks.
All right, thank you, Kathy. We'll go ahead and keep the same system in place. Stu's only got about another 5 or 10 minutes, and we'll go to Katja first, and then we'll go over to Bethany. If you want to go ahead and post your question in there, we'll let Stu answer that for you.
11 parachutes. So, yeah, 11 parachutes. 3 of them on the forward bay cover. The forward bay cover sits on top of the vehicle. Its job is to protect the top of the vehicle from reentry heating and other function, just other environments. Those 3 inflate and take the cover off. Basically, inflate and put the cover in tension. Some thrusters fire, and it just yanks it, gets it off the vehicle, gets it out of the way. So there's 3. The other 2 are the 2 drogue parachutes, and then you've got so that gets you to 5. There are 3 pilot parachutes, which are small parachutes about 8 feet in diameter that are mortar deployed. They go out of the vehicle, and as they go out and inflate, they are tethered to the 3 large main parachutes, and they pull the parachutes out of the bay, and so that gets you to 11. And so we use them all. We don't have any backup. The system's designed such that if one of the 3 main parachutes didn't work for some reason, you still land safely under 2.
All right, Bethany, you're up next.
So actually back, and again, this is one of those videos that's out there on our Facebook page. It used to be in the chart package, how you test the launch abort system. We tested so the launch abort system has 3 individual motors, the abort motor, the jettison motor, and the steering motor. Each one of those was individually tested in their lab settings, or actually in their test cell. And then back in 2010, we built a boilerplate vehicle, made it the proper size and shape and weight, and simulated a pad abort, gave the command for the launch abort system to fire. And this was done out at White Sands, sorry, mixing my tests, out of White Sands out in New Mexico, and it flew an abort profile. The vehicle got to about a mile in the atmosphere in about 2.5 seconds. the astronauts, had there been any in there, would have seen about 12 Gs. It actually spins around, separates off the vehicle, and the vehicle lands. So we've actually done that test. And then you will also, in the computer labs, test the various sensors. And you'll have a command, or you'll have something simulating the rocket, and you tell that simulated rocket to start to fail, and the computers have to sense that and just give you a computer feedback that says, hey, that was a real failure, that was a false failure, and go through all that voting logic. But at the end of the day, like I said, we did that one abort test, and our budget and our plan has us doing another high altitude abort test after EM1.
Zacharias, you're up next.
Personal do on a resume. Oh gosh. Let's see. So, I'm not sure if I can give you a specific. I can tell you that a lot of the folks I work with, when they're looking for somebody, or looking for somebody that knows how to solve a problem, right? So it could be any kind of you pick your activity, but if you know how to logically gather the info and make the decision when you need to, versus not making it too early or making it too late, right? Gather the info and make the decision, and for that matter, lead a team. That tends to be the type of individuals that show up here. Not a lot of. It's interesting when I talk about one of the challenges in project management around here. One of the challenges for us, for folks like me, is that most of the engineers we work with are all type A, not necessarily type A personalities, strong personalities, know their stuff, know their stuff, and so sometimes they're a challenge to lead, right? So we've got folks that, I do a lot of cat herding is one of the ways I describe what I do. But so the engineers that are out there that have demonstrated, I can take this problem and I can run with it and solve it, whether that be work demonstrated or even related extracurricular activity. If you've shown you know how to organize, heck, if you can organize a church committee, you've probably got a chance.
All right, one or two more questions. Let's go to, let's see, David is up next. There you go.
So the way we talked about EFT1 was about $300 million, $350 million, and that's the cost that we spent on the unique hardware and the unique cost of buying the rocket that we bought. Our annual budget, and so it's hard to compare how much EM1 is going to cost, because you start talking about, are you looking at just the cost of the vehicle and of the assets, or of all the design work that goes into it? And so our talking point was, call it $350 million for EFT1. Our annual budget, which is public knowledge, is just under $1 billion a year. So our burn rate is about $1 billion a year, and that covers everything. And it seems like an amazingly large budget until you look at how many different pieces are out there and how much testing you need to do to prove that this vehicle is really going to be safe by the time we fly and put astronauts in it. So I'll give you both comparison points. All right.
All right, Christian, you're up next. This is probably going to be the last question.
All right, yes. Sounds like a plan. Most risky part of the mission. Ascent is risky in the sense that you're sitting on top of a massive booster, and when things go wrong, they go wrong fast. That's really the reason we added the launch abort system. So that gives them a great safety capability and the ability to get out of trouble. And then re-entry and landing. Actually, the highest risk item we have on the program are my parachutes. And it's not because we haven't done a good job on them. It's just you've committed to landing, and you're good. Once you've started, Gravity doesn't take any time off, and so if for some reason the chutes don't come out right, you're going to come in at terminal velocity, and that's an unforgiving event. And so that's probably the riskiest, at the end of the day, the riskiest part of the mission, because on orbit there's definite risks, but you usually have time to react to them. It ends up being the events that when something goes wrong and you don't have time to react, those are the ones we consider our high-risk events. All right, we probably, particularly anybody out there that's on the East Coast, you've got a little football game that we all got to be going to pretty soon. And so, hey, thanks everybody for taking the time. Pop us questions on our Facebook page or any other. You keep peppering us with questions, and for a government group, we're pretty good about getting back, having I think an interesting Facebook page or Twitter page. So pop us notes on those links, and we'll always answer you. Have a great night.
All right, folks, thank you very much. Don't forget to join us next week for our next subject matter expert talk. We'll have updates on Moodle, and we'll see you guys soon. Take care. Bye.